Hello there, and welcome to Beyond the Cosmos, where the biggest questions about space and science and the human future are explored at the pace of a slow breath, where curiosity is never rushed, and where the universe and our place within it unfolds one careful thought at a time. Tonight, we are going to stay a little closer to home than usual. We are not going to travel billions of light years to some distant void or some extraordinary cosmic structure. Tonight, we are going to travel to our nearest planetary neighbor, a cold, rusty, wind-scoured world that has occupied the human imagination for centuries, and that is, in recent decades, beginning to occupy the human ambition in a more concrete, more serious, and more complicated way. We are going to think about Mars, and more specifically, we are going to think about the people who will go there first, about the extraordinary nature of that journey, about the genuine considered possibility that the first human beings to set foot on Martian soil may never return to the world that made them, and about what all of this means, not just technically and scientifically, but personally, philosophically, and in terms of what it tells us about our species and our relationship to the vast, indifferent, extraordinarily compelling universe we find ourselves living in. This is not a pessimistic story. At least, it is not meant to be. It is an honest one, and there is a significant difference. Honesty about the difficulty and the permanence of certain choices does not diminish the choice. Often, it deepens it, and the possibility that the first humans to reach Mars may never come back, when examined carefully and without flinching, is one of the more genuinely profound and genuinely moving possibilities that the near future of our species holds. Before we set off, I want to ask where you are tonight. Perhaps you are in bed, the room dark around you, the day behind you. Perhaps you are somewhere with a window, and if you looked up through it, you might see a night sky, and somewhere in that sky, depending on the season and the hour, there might be a faint reddish point of light that is Mars. Wherever you are far closer to that point of light than any human being has yet traveled. But perhaps not for much longer. If this kind of careful, unhurried exploration of space and the human story within it brings you something worth carrying into rest, it would mean a great deal if you tapped the like button or subscribed to Beyond the Cosmos. It helps other people who need a calm voice to think alongside find their way here. Now, settle into wherever you are. Take one slow breath in and let it out without hurry. And let's begin. Let's start with the simplest possible version of the problem, stated as plainly and as honestly as physics and engineering allow. Mars is approximately 225 million kilometers from Earth when averaged across both planets' elliptical orbits, though this distance varies enormously depending on where both planets are in their respective orbits around the Sun. At their closest, the two planets come within about 54 million kilometers of each other. At their farthest, they are separated by more than 400 million kilometers. A mission to Mars is, by necessity, planned around the orbital dynamics of this varying distance, launched during specific windows, called launch opportunities or opposition windows, when the alignment of the planets makes the journey as efficient as possible. The journey itself, using the most efficient trajectories available to currently conceivable spacecraft, takes between 6 and 9 months each way, depending on the specific trajectory chosen and the technology used. A mission that departs Earth during one launch window, travels to Mars, conducts operations on the surface, and then waits for the next suitable launch window to return would require a total duration of somewhere between 18 months and 3 years from departure to homecoming. Some mission architectures compress this, some extend it. But no realistic scenario, using physics that actually exists rather than physics that has been imagined for science fiction, makes the round trip substantially shorter than this. This is already a long journey by any human standard. The longest single continuous space mission on record, as of the mid-2020s, involves stays of roughly 1 year aboard the International Space Station, and those missions occur in the relative proximity of low Earth orbit, where emergency return is possible within hours, and where communication with Earth involves no meaningful delay. Mars is neither of these things. Emergency return from Mars is not possible within hours or days or even weeks, And communication with Mars, because light itself takes between 3 and 22 minutes to travel the varying distance, means that every transmission, every request for help, every report of a problem, every acknowledgement of a solution arrives at a significant delay in each direction. Real-time conversation is physically impossible. Every decision made on Mars must ultimately be made by the people who are on Mars. So the journey is long. The return window is constrained by orbital mechanics, and the people on the surface are, in a genuinely important sense, truly on their own. This is the basic physical situation before we have even begun to address the biological challenges, the psychological challenges, the engineering challenges, or the existential dimension of what such a journey would mean for the human beings who undertake it. Let's start with the simplest possible version of the problem, stated as plainly and as honestly as physics and engineering allow. Mars is approximately 225 million kilometers from Earth when averaged across both planets' elliptical orbits, though this distance varies enormously depending on where both planets are in their respective orbits around the Sun. At their closest, the two planets come within about 54 million kilometers of each other. At their farthest, they are separated by more than 400 million kilometers. A mission to Mars is, by necessity, planned around the orbital dynamics of this varying distance, launched during specific windows called launch opportunities or opposition windows, when the alignment of the planets makes the journey as efficient as possible. The journey itself, using the most efficient trajectories available to currently conceivable spacecraft, takes between 6 and 9 months each way, depending on the specific trajectory chosen and the technology used. A mission that departs Earth during one launch window, travels to Mars, conducts operations on the surface, and then waits for the next suitable launch window to return, would require a total duration of somewhere between 18 months and 3 years from departure to homecoming. Some mission architectures compress this, some extend it. But no realistic scenario using physics that actually exists rather than physics that has been imagined for science fiction makes the round trip substantially shorter than this. This is already a long journey by any human standard. The longest single continuous space mission on record, as of the mid-2020s, involves stays of roughly 1 year aboard the International Space Station, and those missions occur in the relative proximity of low Earth orbit, where emergency return is possible within hours, and where communication with Earth involves no meaningful delay. Mars is neither of these things. Emergency return from Mars is not possible within hours or days or even weeks. And communication with Mars, because light itself takes between 3 and 22 minutes to travel the varying distance, means that every transmission, every request for help, every report of a problem, every acknowledgement of a solution arrives at a significant delay in each direction. Real-time conversation is physically impossible. Every decision made on Mars must ultimately be made by the people who are on Mars. So the journey is long. The return window is constrained by orbital mechanics, and the people on the surface are, in a genuinely important sense, truly on their own. This is the basic physical situation before we have even begun to address the biological challenges, the psychological challenges, the engineering challenges, or the existential dimension of what such a journey would mean for the human beings who undertake it. Before we go further, let's spend some time with the people who might actually go, because any honest exploration of this subject has to honor the human reality of it, rather than treating the crew as abstract variables in an engineering problem. The people who will travel to Mars first will not be drafted. They will be volunteers, and by all accounts of those who study the psychology of extreme exploration and those who have already expressed willingness to go, they will be volunteers who understand perfectly well what they are signing up for. The history of exploration is full of people who chose, deliberately and with open eyes, to go somewhere extraordinarily difficult and extraordinarily dangerous, knowing that return was not guaranteed and accepting that risk as the price of the extraordinary thing they were choosing to do. Ernest Shackleton's famous advertisement for Antarctic expedition crew, whether the specific wording is historically accurate or somewhat legendary, captures something true about the psychology of extreme explorers. Hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return, doubtful, honor, and recognition in case of success. People answered that advertisement. People have always answered that advertisement in every era and every culture when the call goes out for those willing to go somewhere genuinely difficult and genuinely unknown. The astronauts and cosmonauts who have flown to orbit already understand something of this calculus. Every launch carries risk. The history of human spaceflight includes 14 people who died during missions aboard Challenger and Columbia, and 3 who died in the Apollo 1 fire on the launch pad. Every person who straps into a spacecraft does so understanding, at least abstractly, that the vehicle might not bring them home. But Mars raises this calculation to a different order of magnitude because the distance is so much greater, the journey so much longer, the rescue so much more impossible, and the window for return so much more constrained. People who study the psychology of long-duration isolation and exploration have thought carefully about what kind of person can sustain years of confinement in a small space, separated from everything familiar, facing genuine daily danger, and performing high-stakes technical work while doing so. The characteristics identified tend to include emotional stability, high tolerance for uncertainty, strong collaborative instincts combined with genuine individual competence, the ability to find meaning in the work itself rather than in external validation, and a particular relationship with risk that is neither reckless nor paralyzing. These are not common characteristics. They describe a specific kind of person, and among those people, a subset will emerge in whatever era the first Mars mission becomes possible, who look at the distance and the danger and the possibility of never returning and decide that going is worth more to them than staying. The question of what it means for a human being to make that decision, with full knowledge of the probability distribution of outcomes, is one of the more interesting and more important questions this topic raises. Let's think carefully about what the one-way possibility would actually mean in practice, because it is easy to speak of it abstractly, but considerably harder to hold clearly in the mind. Imagine being selected for the first crewed Mars mission. You have spent years preparing, training for the specific physical and technical challenges of the journey and the surface. You know the timeline: 6 to 9 months of travel in a confined spacecraft, then surface operations for whatever duration the mission calls for, then a wait for the return window, then months more of travel home. You know that the return depends on systems that have never been tested in exactly these conditions, on fuel that has been sitting in a tank on another planet for however long since it arrived, on a rocket that has been exposed to Martian radiation and temperature cycles and dust storms for the duration of your stay. You know that if any of these things fail catastrophically enough, you are not going home. How do you live with that knowledge? The answer, from the psychology literature on extreme exploration and from conversations with astronauts and with the people who support them, is that you compartmentalize it to some degree. Not by denying it, but by acknowledging it fully and then choosing again to proceed. The knowledge of the risk is integrated into the identity of the explorer rather than sitting outside it as a threat. The person who goes to Mars first will have, in some sense, already accepted the possibility of not returning, not as a resignation to fate, but as a conscious, considered choice that the experience of going is worth more than the guarantee of coming back. This kind of choice has analogues throughout human history, even if none of the analogues are perfectly precise. The sailors who crossed uncharted oceans in wooden ships did not have guaranteed return. The early aviators who pushed the boundaries of what aircraft could do did not fly with guaranteed survival. The mountaineers who pushed into the death zone on the world's highest peaks knew that altitude and weather and the limits of human physiology could conspire to keep them there permanently. In each case, the people who chose to go did so with some version of the same understanding. The thing at the end of the journey is worth the risk that you might not come back from it. What makes Mars different from all of these analogues is the scale of the distance and the permanence of the isolation. A sailor who runs into trouble in uncharted waters is still on the same planet as the people who might eventually find them. A mountaineer who turns back from the summit is an hour or a day or a week from base camp and eventually from civilization. A person stranded on Mars is 225 million kilometers from the nearest other human beings, separated by a journey that takes months even under optimal conditions, in a place where no search and rescue has ever occurred and where the idea of rescue, at least with anything resembling current technology, is essentially fiction. This is not a metaphor for isolation. This is a new kind of isolation that the human species has never actually experienced before, even in all the long history of exploration and adventure and deliberate, dangerous choice. There is a specific and important distinction that matters in this conversation, and it is between the practical impossibility of return and the physical impossibility of return. These are different, and being clear about which one applies in which circumstances matters for understanding the honest version of tonight's title. The physical impossibility of return from Mars is not quite the permanent, absolute kind of impossibility we explored in our episode about leaving the local group. The laws of physics do not forbid a rocket launched from Mars from reaching Earth. The planets are close enough by cosmic standards that the journey is well within the laws of orbital mechanics and well within the capacity of rocket propulsion, given sufficient fuel and sufficient engineering. Mars is not causally disconnected from Earth in the way that distant galaxy clusters are causally disconnected from our local group. A return trip from Mars is physically possible. What makes the return genuinely, potentially impossible for the first explorers is a combination of practical factors, each of which is individually serious and collectively formidable, and each of which operates under the additional constraint that the margin for error on another planet with no support infrastructure and no history of operations is essentially zero. The fuel problem is real and significant. Any fuel needed for the return journey must either travel with the crew or be sent ahead, and in either case represents an enormous engineering and logistical challenge. The window problem is real and significant. The specific orbital alignment required for an efficient return journey occurs only periodically, and missing a window means waiting considerably longer for the next one, which may not be compatible with the life support reserves available. The vehicle reliability problem is real and significant. Every component of a return vehicle has a failure probability, and the aggregate probability of at least one critical failure across a mission of this complexity and duration is not trivially small. The human health problem is real and significant, and we will explore it in detail shortly. The radiation problem is real and significant. The communication delay problem, while it does not directly prevent return, means that any crisis must be managed without real-time ground support from the most experienced engineers and flight controllers on Earth. None of these problems is individually unfixable. Human ingenuity has, historically, fixed problems of similar categories when given sufficient time, resources, and determination. But the first Mars mission will necessarily occur before all of these problems have been fully fixed. simply because we will not know with certainty what we have failed to anticipate until we are actually there. The history of exploration is a history of encountering the unexpected, and the unexpected, when it occurs 225 million kilometers from Earth with a crew of perhaps 4 to 6 people and no rescue possible, carries consequences that are qualitatively different from the unexpected in any previous human exploration context. Let's spend careful time now on the biological challenges, because the human body is one of the most significant and most underappreciated obstacles to a successful round-trip Mars mission. And understanding what the journey does to the people making it is essential for understanding why the "may never come back" of tonight's title is not hyperbole. Begin with the journey itself. 6 to 9 months in microgravity, the near weightlessness of interplanetary space, is known from extensive experience on the International Space Station to produce significant changes in the human body. Muscles atrophy without the constant resistance of gravity to work against. Bones lose density at a rate comparable to severe osteoporosis. The cardiovascular system changes its fluid distribution, with fluid shifting upward toward the head in ways that affect vision, intracranial pressure, and the overall function of the cardiovascular system. The immune system is altered in ways not fully understood. The microbiome, the community of bacteria and other microorganisms that inhabit every human body and contribute to its function, shifts in response to the microgravity environment and the reduced diversity of an enclosed spacecraft. Astronauts returning from long-duration missions on the International Space Station, typically around 6 months in duration, require weeks to months of rehabilitation before they can walk normally, before their cardiovascular system readjusts to the demands of a full-gravity environment, and before the various other physiological changes induced by microgravity have substantially reversed. The longer the mission in general, the more pronounced these effects, and the longer the recovery. A crew arriving at Mars after 6 to 9 months in microgravity will arrive in a condition significantly weaker than when they departed. Mars's gravity, at 38% of Earth's, is not microgravity. It is enough gravity to impose meaningful physical demands on a crew that has spent months losing bone density and muscle mass. The first tasks a Mars crew will face after completing the most technically demanding landing in human history will need to be performed by human beings whose bodies are somewhat compromised by the very journey that brought them there. Then there is the radiation. Earth is protected from the most harmful forms of cosmic radiation by its magnetic field and its atmosphere. The International Space Station in low Earth orbit still benefits from substantial protection from Earth's magnetic field. In interplanetary space, between Earth and Mars, there is essentially no such protection. The galactic cosmic rays that permeate interplanetary space, along with the less predictable but more intense bursts of solar energetic particles that the Sun periodically releases, represent a radiation environment that has no clear analog in the history of human space travel. The cumulative radiation dose received during a round-trip Mars mission, including the transit and surface stay, is estimated to exceed the career limits currently established for NASA astronauts, based on the agency's acceptable risk thresholds for radiation-induced cancer. This is a significant fact. A round-trip Mars mission, by current standards and with current technology, would expose its crew to radiation levels considered excessive by the safety criteria of the most experienced space agency in history. The surface of Mars offers partial protection, since the planet provides shielding in one direction, but the thin Martian atmosphere provides very little additional protection compared to Earth's thick atmosphere, and the transit remains essentially unavoidable. Long-term radiation exposure at these levels raises the risk of cancer, of cognitive impairment, of damage to the central nervous system, and of other biological effects that are still being actively studied. A crew that completes a Mars mission and returns to Earth may return with a significantly elevated lifetime risk of cancer and other radiation-related health effects, and the crew members themselves may experience cognitive changes during the mission that affect their ability to make the complex decisions that mission success requires. Let's think now about the psychological dimension, which is, in some ways, even less well understood than the biological one, and which presents some of the most genuinely novel challenges a Mars crew will face. Human beings are social animals, evolved over hundreds of thousands of years for small group living within reach of a larger community. We are not well designed for isolation, particularly not for the specific combination of extreme confinement, high stakes, and unresolvable separation from everyone and everything outside a few square meters of living space. The psychological effects of prolonged isolation in confined environments have been studied in Antarctic winter overcrews, in submarine crews, in long-duration spaceflight crews on the ISS, and in dedicated isolation studies designed to simulate aspects of a Mars mission. The findings are consistent and concerning. Sleep disorders emerge, mood disturbances emerge, interpersonal conflicts in the small group can escalate in ways that would be manageable in an ordinary environment, but that become much more serious when there is no physical escape from the other people in the conflict, and when the consequences of unresolved conflict include potential mission failure. Cognitive performance declines in ways that affect concentration, decision-making, and the performance of complex technical tasks. The psychological phenomenon, sometimes called the third quarter effect, in which a meaningful dip in mood and motivation tends to occur roughly 3/4 of the way through an isolated mission, has been documented across many different kinds of confined isolation. For a Mars crew, these challenges are compounded by factors that do not apply to any previous human isolation study. The communication delay means that the crew cannot have real-time support from loved ones, from mission control, or from mental health professionals on Earth. Every message from home, every supportive voice, every piece of news from the larger world arrives with a delay of between 3 and 22 minutes each way, making the kind of immediate emotional support that humans normally rely on in difficult moments simply unavailable. The crew will manage every crisis, every interpersonal conflict, every moment of despair or fear, largely on their own or with support from each other, which is itself a resource that can be depleted. There is also the particular psychological weight of knowing what the crew knows, that they are farther from any other human being than any human being in history has ever been. That if something goes seriously wrong, there is no help coming, and that the journey home requires everything to go right across a chain of events that stretches over months and years. Carrying this knowledge day after day for the duration of a mission measured in years, while also performing technically demanding work and maintaining the interpersonal cohesion of a small group under pressure, is a psychological burden with no historical precedent. None of this means that the people selected for a Mars mission will be unable to handle it. They will be selected precisely because they show the capacity to handle it, and they will be supported by every possible form of preparation and mission design that experience and ingenuity can provide. But the genuinely honest statement is that we do not know with confidence exactly what sustained exposure to this specific combination of stressors will do to specific individuals over the duration of a Mars mission. We are extrapolating from analogues that approximate the relevant conditions but do not fully replicate them. Let's turn now to a possibility that has been seriously and publicly discussed by space agencies, aerospace companies, and the researchers who think about Mars missions professionally: the deliberate one-way mission. Not a mission that becomes one-way due to some failure, but a mission designed from the outset to be one-way, in which the crew goes to Mars understanding and accepting that they are going to stay. This might sound extreme, and there are genuine ethical dimensions to it that deserve careful attention. But the arguments for a deliberate one-way design are not trivial, and understanding them changes the emotional texture of the conversation about whether the first Mars explorers might never return. The core argument for a deliberate one-way mission is one of mass and resources. The single biggest engineering challenge in a return trip Mars mission is the requirement to carry, send ahead, or manufacture on Mars the fuel and vehicle for the return journey. Remove that requirement, and the mission becomes dramatically more mass efficient, potentially enabling a mission that is either significantly cheaper, significantly larger in terms of crew and equipment delivered to the surface, or both. A one-way mission that lands 4 people with extensive equipment and years of supplies may be more achievable with technologies available in the near term than a return mission that lands 2 people with limited equipment and a return vehicle. The second argument is one of commitment and infrastructure. If the first Mars mission is designed as a one-way settlement rather than as a brief visit followed by a return, it creates the conditions for genuinely establishing a presence on Mars rather than simply touching it and leaving. A crew committed to staying can build and improve and expand their presence in a way that a crew preparing for a fixed duration stay and an imminent return cannot. The settlement logic holds that the first humans on Mars should be the first Mars settlers, people who go to begin something rather than people who go to visit somewhere. The third argument is one of analogy to historical exploration and colonization. Many of the human migrations and expansions throughout history were, functionally, if not always deliberately, one way. The first people to cross land bridges into new continents did not return to their origin points. The settlers of remote islands throughout the Pacific crossed enormous distances in small boats with no realistic prospect of returning to where they came from. The early colonists who left Europe for the Americas in the 16th and 17th centuries understood that they were likely leaving forever, that the journey was not a visit, but a permanent relocation. In each case, people made that choice, and the consequences were, over long timescales, among the most significant in human history. Whether this analogy is fully apt, and whether the deliberate one-way mission is ethical in specific ways that the historical migrations may not have been questioned on, are genuine and important questions. But the analogy does help place the one-way Mars mission within a human pattern that is older and wider than the space age. The ethical dimension of the one-way mission deserves its own careful exploration because it is not simple and it is not dismissible. The most immediate ethical concern with a deliberate one-way mission is one of consent and its limits. An adult who consents to a one-way mission, fully informed of what that means, is exercising their autonomy in a way that should, in principle, be respected. Adults are allowed to make irreversible decisions about their own lives. People join militaries knowing they may die in service. People climb extreme mountains knowing they may die doing so. People smoke and drink and skydive and race motorcycles and choose careers as firefighters and police officers and emergency medical workers. The autonomous adult has always been permitted within a broad range to exchange safety for experience, longevity for meaning, comfort for purpose. But the specific irreversibility of a one-way Mars mission, compared even to these other risky choices, raises genuine questions. The person who goes to Mars on a one-way mission is not just accepting a heightened risk of death. They are accepting the certainty of permanent separation from Earth, from everyone and everything they love there, from the physical world their entire existence has been shaped by. They are choosing a form of exile that, unlike any voluntary exile in human history, cannot be ended by returning. The distance and the physics make the exile absolute. This is a genuinely novel form of decision, and it is worth taking seriously the question of whether any amount of counseling and preparation can fully equip a person to consent to something so completely without precedent in human experience. There is also the question of what happens to the Mars settlers as time passes and circumstances change. A person who consents to a one-way mission at age 35, brimming with commitment and prepared for the challenge, may feel quite differently at age 45 or 50 or 60 after years of Martian hardship and loss and the slow weight of permanent separation. The person who consents to the mission is not identical to the person who eventually lives with its consequences, and the person who eventually lives with its consequences has no recourse. They cannot change their mind in a way that matters because the means of changing their mind, of coming home, does not exist. This is a genuine ethical complication, and the fact that it resembles some of the ethical complications of other life choices: marriage, parenthood, the taking on of permanent responsibilities, does not make it go away. It simply places it in a human context where we recognize that permanent choices have permanent consequences, and that the person who makes the choice and the person who eventually lives with it may be, in important ways, different people. The space agencies and private organizations that are seriously planning Mars missions are, it is worth noting, generally committed to the round-trip design as a matter of both engineering goal and ethical commitment. The loss of life that a failed one-way mission would entail, the death of explorers stranded on Mars with no rescue possible, is a scenario that everyone in the field hopes to avoid through sufficient engineering redundancy and preparation. The possibility of accidental one-way missions, rather than deliberate ones, is perhaps the more honest version of tonight's title. Let's spend considerable time now with the question of what the surface of Mars is actually like, because any honest discussion of people living and working there, whether temporarily or permanently, has to be grounded in the reality of the environment rather than the simplified version that often appears in popular accounts. Mars is a desert world of extraordinary grandeur and extraordinary hostility. It is a planet slightly more than half the diameter of Earth, with a surface area roughly equal to the land surface of Earth, all of it continuous solid ground, since Mars has no oceans. Its surface is ancient and varied, vast plains of dark volcanic rock, enormous canyon systems that would stretch across an entire continent on Earth, towering shield volcanoes including Olympus Mons, the largest known volcano in the solar system, polar ice caps composed of water ice and carbon dioxide ice, and the characteristic rust-red color that comes from iron oxide, ordinary rust, in the surface dust. The atmosphere is thin, about 1% of Earth's sea-level atmospheric pressure, and composed primarily of carbon dioxide with small amounts of nitrogen and argon and trace quantities of other gases. This atmosphere is far too thin and far too lacking in oxygen for human beings to breathe, and it provides far too little atmospheric pressure to allow liquid water to persist at the surface at most temperatures. The thin atmosphere also provides very little protection from ultraviolet radiation from the Sun and from the galactic cosmic rays we discussed earlier. Surface temperatures vary enormously. At the equator on a summer day, afternoon temperatures can briefly reach the high end of what a lightly dressed person might find cool but tolerable, perhaps a few degrees above 0 Celsius in rare conditions. But nights drop to minus 70 or 80 Celsius. At the poles, temperatures can reach minus 125 degrees Celsius. The daily temperature swing from the warmest part of a Martian afternoon to the coldest part of a Martian night can exceed 100 degrees Celsius at some locations. No human being can exist on the Martian surface without a pressure suit providing breathable air at adequate pressure, thermal protection against extreme cold, and protection from radiation. The dust is a particular and underappreciated challenge. Mars is covered in fine, pervasive, iron-rich dust that the thin atmosphere can lift into enormous dust storms capable of covering the entire planet for weeks at a time. This dust is not merely inconvenient. It coats solar panels, reducing power generation. It works its way into mechanical systems. It is potentially toxic. The specific chemistry of Martian dust, including the presence of perchlorates, chemical compounds that are hazardous to human health, adds an additional layer of concern for any crew spending extended time in an environment where dust contamination of the habitat is essentially unavoidable over long periods. The Martian day, called a sol, is about 24 hours and 37 minutes, remarkably close to an Earth day, which has led some researchers to suggest that humans might adjust to the Martian day cycle relatively comfortably. But the longer-term implications of living on a planet whose seasonal cycle, orbital period, and distance from the Sun are all substantially different from Earth's, including the longer Martian year of about 687 Earth days and the different character of Martian seasons, are less certain in their effects on human biology and psychology. Now let's think about what living on Mars would actually look like for the first inhabitants, whether those inhabitants are planning to stay temporarily or permanently. A Mars habitat, at least in the early phase of any mission, will be a confined structure, either brought from Earth or assembled from pre-delivered components, with a volume considerably smaller than even the Spartan quarters of a long-duration ocean voyage. The crew will live in pressurized environments that maintain Earth-like atmospheric conditions with carefully managed air composition, temperature, humidity, and pressure. These environments will need to be maintained continuously because any significant breach of pressure could be rapidly fatal. The daily routine will be largely structured, necessarily. Life support systems need monitoring and maintenance. Equipment needs to be checked and repaired. Scientific work needs to be conducted. The habitat and any external structures need inspection and upkeep. Food needs to be prepared from whatever supplies are available, either delivered from Earth or, increasingly in longer stay scenarios, grown on site. Communication windows with Earth need to be utilized, accepting the inherent delay. Sleep schedules need to be maintained for health and operational reasons. Exercise needs to be built into every day to counteract the effects of Martian gravity on muscles and bones, which at 38% of Earth's is better than the near-zero gravity of space travel, but still significantly less than what human bodies evolved for. Excursions outside the habitat, what might be called Martian EV. As by analogy to the extravehicular activities of current space missions, will require suiting up in pressure suits, going through airlock procedures, and operating under all the constraints of working in a hostile environment in a suit that limits dexterity, range of motion, and the amount of time that can be spent outside before life support is exhausted. The suits will be heavy, pressurized garments far more restrictive than ordinary clothing, and they will need to be kept in excellent condition since any significant failure outside the habitat would be life-threatening. The first Mars base, for however long it exists in its early form, will be a place of routine punctuated by intensity. Most days will be spent in a carefully managed routine of maintenance, science, and preparation. Occasionally, something will go wrong that requires immediate, creative problem-solving with whatever resources happen to be on hand, because the nearest spare part warehouse is 225 million kilometers away, and the nearest human expert in whatever system just failed is separated by a 22-minute communication delay that makes real-time troubleshooting support literally impossible. This is life on Mars, at least in its earliest form. It is demanding, dangerous, isolating, and, for the specific kind of person drawn to it, potentially profoundly meaningful in a way that no ordinary life can quite replicate. Let's think now about a particular and genuinely important question. that any serious account of the first Mars missions must eventually address. What happens to someone who gets seriously ill or seriously injured on Mars? Medical care on Mars will be limited to whatever has been brought and whatever the crew members themselves have been trained to provide. The crew will almost certainly include at least one person with substantial medical training, possibly one or more physicians, but even the best-trained Mars medical officer will face scenarios that challenge everything they know and everything they have available. Some medical conditions can be managed well with limited equipment and limited pharmaceutical supplies. Minor infections treatable with antibiotics, manageable injuries, conditions that respond to rest and supportive care. But a significant traumatic injury requiring surgery and intensive care and blood transfusions and a sterile operating environment and specialist involvement poses challenges that no amount of medical training and no reasonable quantity of supplies can fully address. A cardiac event requiring advanced resuscitation and invasive cardiac intervention in a patient whose physiology has already been altered by months of microgravity and radiation exposure is a scenario for which no good plan exists, because no good plan is currently possible. More to the point, sending someone home from Mars who needs advanced medical care is not possible on any timescale consistent with keeping them alive. The months-long journey back, even if a return vehicle were immediately ready and the launch window perfectly timed, would be incompatible with the care required by most serious medical emergencies. The person on Mars who has a severe medical crisis that cannot be managed with the resources on hand is, in the most direct and most honest terms, unlikely to survive regardless of what decisions are made about the mission. This is one of the hardest aspects of early Mars missions to think about honestly, because it means that the people who go there are accepting not just the general risk of the journey, but the specific risk that if their bodies fail in certain ways, in this specific location, those bodies will not be coming home even if they are still alive at the moment of failure. The medical risk on Mars is not merely a risk of death. It is a risk of the specific kind of dying that occurs when the care required is simply not available and cannot be made available. Space agencies take this seriously and design their missions to reduce this risk as much as possible through crew selection, extensive medical training, comprehensive medical kits, and telemedicine support from Earth, even accounting for the communication delay. But the fundamental limitation remains. Mars is a long way from Earth, and medicine is not a thing you can teleport. Let's spend time now thinking about the question of resources and self-sufficiency, because one of the most important variables in whether the first Mars explorers can return and in what kind of life they live on Mars if they stay is the extent to which they can produce what they need from the Martian environment, rather than depending entirely on supplies from Earth. The concept of in situ resource utilization, generally referred to by the acronym ISRU in the engineering literature, encompasses a broad range of technologies designed to convert Martian materials into useful substances. Water ice, which exists in significant quantities both at the Martian poles and in the subsurface at various other latitudes, is the most immediately relevant resource. Water can be extracted, purified, and used for drinking, for hygiene, for plant growth, and, through electrolysis, split into hydrogen and oxygen. The oxygen produced this way can be used for breathing. The hydrogen can potentially be combined with carbon dioxide from the Martian atmosphere to produce methane, a fuel that could, in principle, be burned in a rocket engine to power a return launch from Mars. This last possibility, manufacturing rocket fuel on Mars from Martian resources, is one of the more compelling and more widely discussed ISRU applications because it addresses directly the mass problem that makes the return journey so difficult. If a mission can land on Mars with the hardware needed to produce its own return fuel rather than having to carry that fuel from Earth, the mass requirements for the mission are dramatically reduced. SpaceX, in its public mission architecture for Mars, has placed ISRU-based fuel production at the center of its plan for making Mars missions economically and logistically feasible. The technology to produce fuel on Mars this way, called the Sabatier process, when used to combine hydrogen and carbon dioxide into methane, is not exotic. It is well understood chemistry that has been demonstrated in laboratory settings on Earth. The challenge is scaling it up reliably, autonomously, in the Martian environment over the period of time required to produce sufficient fuel for a return journey. This requires robust, reliable hardware operating in cold temperatures, dust-laden air, and without human maintenance or attention during the period before the crew arrives. It requires power, which on Mars means either nuclear power or solar power that needs to function continuously through dust storms that can dramatically reduce solar input. And it requires that the resulting fuel is stored safely for the duration of the crew's stay, without losses that would compromise the return capability. None of these challenges is insuperable, but each represents a genuine technical hurdle that needs to be cleared reliably, not just in ideal conditions, but in the specific, variable, sometimes adversarial conditions of the actual Martian surface, in order for the return fuel to be available when the crew needs it. Let's think carefully about the time frame. When might the first humans actually reach Mars? And what does that timing imply about the level of technology available to them? This is a question where educated prediction is genuinely difficult because the time frame depends heavily on political will, on funding levels and funding continuity, on the relative progress of competing approaches by national space agencies and private companies, and on technical achievements that are still underway and whose timeline is uncertain. As of the mid-2020s, SpaceX has publicly stated ambitions for crewed Mars missions in the 2020s to 2030s timeframe, a timeline that many independent observers consider optimistic given the scale of the remaining technical challenges. NASA's longer-range plans have repeatedly included Mars as a long-term goal, though specific crewed Mars mission timelines from NASA have shifted repeatedly over the decades as funding priorities and program architectures have changed. Other national space agencies, including those of China and others, have expressed Mars ambitions at various levels of concreteness. What seems relatively likely, based on the trajectory of Mars mission planning in the 2020s, is that the first crewed Mars mission occurs somewhere in the 2030s to 2050s window, though dates beyond this range are certainly possible, and dates earlier than 2035 seem to require extraordinary acceleration of technical progress and funding commitment. This timing matters for tonight's discussion because it sets the technological context in which the first mission occurs. A crewed Mars mission in the 2035 to 2040 timeframe would be conducted with technologies that are largely extensions of what exists today. Rockets that are substantially more capable than current launch vehicles, but not fundamentally different in their underlying physics, life support systems drawing on decades of ISS experience, but still based on broadly similar principles, and medical capabilities on par with or slightly better than current technology. A mission in the 2050s or beyond might incorporate technologies that are genuinely more advanced, but the specific trajectory of technological development over that period is genuinely uncertain. The implication for the return problem is that the first Mars mission, whenever it occurs, will likely be conducted at a technological level that makes the return genuinely challenging and genuinely uncertain, rather than comfortable and routine. It will not occur when the technology is so mature that the risk is negligible, because the technology will not reach that level of maturity without someone going first. The first crewed Mars mission is, by definition, the mission that tests the actual combination of all the systems that need to work together in conditions that ground tests can only approximate. There is an important and sometimes neglected aspect of this discussion that deserves its own section, and it concerns what the people on the ground, the mission controllers and engineers and scientists and support personnel will experience as they support the first Mars mission from Earth. Mission control for a Mars mission will be unlike any previous mission control in human history. The fundamental difference is the communication delay, and it changes the psychological and professional reality of the people in that room in ways that the culture of spaceflight has not previously had to contend with on this scale. Every space mission in history has had mission control as the ultimate safety net. When something goes wrong on a spacecraft in low Earth orbit, within a few thousand kilometers of the surface, the people in mission control can respond in real time. The Apollo 13 emergency, in which a catastrophic failure aboard a lunar-bound spacecraft required an improvised creative solution developed and tested in hours, was managed with real-time communication. The crew spoke to mission control. Mission control spoke to the crew, and the back and forth of problem-solving happened at conversation speed. On a Mars mission, real-time communication is physically impossible. The delay means that the crew will have defined the problem, attempted solutions, and either succeeded or failed before any response from Earth can arrive. Mission controllers will listen to reports of a developing emergency and know with certainty that whatever they say in response will arrive after the crew has already had to act or has already been unable to act. The role of mission control becomes different, less emergency response and more long-term planning and analysis, less real-time decision support, and more preparation and training and contingency planning delivered before the crisis rather than during it. This is a profound shift in the psychology and the function of the people who support a human spaceflight mission. And understanding it helps explain some of the reasons why the Mars mission will feel genuinely different from all previous human space missions, not just for the crew on the surface, but for the entire community of people engaged in the enterprise on Earth. Let's spend time now on the scientific case for going to Mars with humans at all, because the argument for accepting all of this risk and difficulty is not merely romantic or ambiguous. It rests on specific, well-defined scientific questions that Mars is uniquely positioned to help answer, and understanding those questions helps explain why so many serious people in so many serious institutions continue to push toward this goal despite the enormous challenges involved. The central scientific question that drives much of the interest in Mars is the question of life. Not life on Mars today in any flourishing or obvious form, but the question of whether Mars was, at some point in its past, a world capable of harboring life, and whether, if life arose there, any remnant of that life persists in some form today. Mars was not always the cold, dry, thin atmosphered world it is now. The geological and chemical evidence accumulated by decades of robotic missions, beginning with the Mariner and Viking missions of the 1960s and 1970s, and continuing through the Mars exploration rovers, the Mars Reconnaissance Orbiter, the Curiosity and Perseverance rovers, and other missions, paints a picture of an ancient Mars substantially different from the present one. Billions of years ago, Mars had liquid water on its surface, possibly in significant quantities. It had a thicker atmosphere. It had geological activity, including volcanism, that could have provided energy sources for microbial life. The basic conditions that, on Earth, gave rise to life in its earliest forms may have been present on Mars for hundreds of millions of years. Whether life arose in those conditions and what happened to it when Mars's climate shifted is a question that robotic missions have approached but not answered. The challenge is that finding genuine evidence of ancient Martian life, if it exists, may require the kind of in situ exploration sample collection, and analysis that robots are limited in their ability to perform. A human geologist on Mars, trained to recognize the kinds of rocks and formations and chemical signatures that preserve evidence of ancient biological activity, equipped with the full range of observational and analytical capabilities of a trained human mind, may be able to accomplish in days what robotic missions take years to approach. Beyond the life question, Mars holds scientific interest in its geology, in its atmospheric science, in its planetary history, and in the clues it holds to the early history of the solar system. Understanding Mars is understanding a planet that followed a different path from Earth, despite starting from broadly similar conditions, and that understanding has implications for our understanding of planetary habitability more generally, and therefore for the search for life beyond our solar system. The scientific value of human Mars exploration is real and substantial. This does not settle the ethical questions about who goes and under what conditions and with what prospects for return, but it provides a genuine, serious justification for the enterprise that goes beyond mere adventure or symbolic achievement. Let's think about a specific and somewhat counterintuitive aspect of the one-way possibility, the extent to which it might actually be, for certain specific people, preferable to the alternative. The assumption embedded in the title of tonight's exploration that not coming back is the bad outcome and coming back is the desirable one is a natural and understandable assumption, but it is not necessarily universal. For a certain kind of person, the prospect of remaining on Mars permanently might not be a tragedy to be avoided, but a purpose to be sought. Consider what it means to be among the first human settlers of another planet, the founding inhabitants of a new world, the people whose footprints are the first human footprints on another planet, who build the first permanent human structures beyond Earth, who experience sunsets on Mars that no human has ever watched, who look up at Earth as a bright point of light in a Martian sky and carry, in their knowledge of that distance, a relationship to the universe that no previous human being has been able to have. There is a profound kind of meaning available in that situation, a meaning that has very little to do with comfort or safety or proximity to familiar things, and a great deal to do with being at the frontier of something genuinely significant. The first permanent Mars settlers, if they exist, would be among the most consequential people who ever lived in a very literal, historical sense. They would be the founders. Whatever civilization eventually develops on Mars, if such a civilization develops, will trace its origins to the people who first stayed. There are people, and there have always been people, for whom this kind of historical and existential meaning is worth more than safety and proximity and the comfort of coming home. Not because they are reckless or because they underestimate the difficulty, but because they genuinely and thoughtfully value the experience and the significance of being there more than they value the return. The psychological profile of such a person is real. The desire to be a founder, to be at the beginning of something genuinely new, has motivated some of the most consequential decisions in human history. For such a person, the question of whether they come back may be at some level beside the point. What matters is whether they get there. What matters is whether they contribute to something that outlasts them. Whether they die on Mars after 20 years of extraordinary frontier life or return to Earth to die in a hospital at a ripe old age is, in this framework, a secondary question compared to what they did during those years. This is a genuinely held perspective among at least some of the people who seriously contemplate Mars exploration, and dismissing it as simple bravado or inadequate appreciation of the risks would be inaccurate. It is a coherent value system that places certain kinds of meaning and certain kinds of historical significance above longevity and comfort. It is, to put it plainly, the same value system that has sent human beings into every genuinely difficult and genuinely dangerous new territory throughout our history. Let's think now about the children question, because it is one that any serious discussion of permanent Mars settlement must eventually engage with, and it introduces some of the most genuinely difficult ethical territory in this entire subject. If Mars is settled permanently rather than visited temporarily, and if the settlement grows in population over time, eventually the Mars population will include children, people who were born on Mars, who have never known Earth, who cannot leave Mars in any practical sense because they have grown up in Martian gravity, and their bones and muscles and cardiovascular systems have been shaped by Martian conditions from birth. What the long-term effects of Martian gravity on a developing human body might be is genuinely unknown. It might be broadly compatible with normal human development. It might produce subtle or significant differences in bone density, in cardiovascular capacity, in neurological development. We genuinely do not know because no human being has ever grown up in Martian gravity. The first children born on Mars will be citizens of a world they did not choose, in an environment that is hostile to their biology by the standards of the planet their species evolved on, separated from Earth by a distance that makes Earth effectively unreachable for anyone who needs Earth-standard medical care or who has developed a physiology shaped by Martian rather than Earth conditions. These children will inherit the consequences of their parents' choice in a way that they themselves have not consented to. This is one of the aspects of permanent Mars settlement that draws the sharpest ethical scrutiny, and reasonably so. The settler who chooses to go to Mars is, in some sense, also choosing for their future children, and possibly for multiple generations of descendants, all of whom will be shaped by a world they were never asked whether they wanted to inhabit. This resembles, in some ways, the situation of children born into any circumstance they did not choose, which is to say, all children everywhere, but the specific circumstances of Mars, the hostile environment, the physical isolation, the genuine absence of the option to leave and go somewhere else, give the analogy a particular sharpness that deserves acknowledgement. None of these considerations necessarily argues against Mars settlement. They argue for taking the ethics of Mars settlement seriously, for thinking carefully about what obligations the first settlers have to the children who will follow them, for designing settlements and societies with the well-being of future generations explicitly in view. The ethical complexity of the question does not make the enterprise wrong. It makes it serious. Let's spend some time now with the long arc of what a successful first Mars mission might mean, not just for the people on that mission, but for the human species and for the trajectory of the species' relationship with the universe. If the first humans who land on Mars survive, if they conduct their mission successfully, if they do whatever combination of exploration and science and habitat building the mission calls for, and if they either return safely to Earth or establish a sustainable presence on Mars, the consequences for subsequent missions are enormous. Every successful human Mars mission makes the next one somewhat easier, not because the physics changes, but because the engineering understanding deepens. The first mission demonstrates what actually works and what doesn't in the specific conditions of Mars, teaches lessons that ground tests and robotic precursors can only approximate, and identifies the specific failure modes and the specific environmental challenges that will shape all subsequent design decisions. The first people on Mars become, by virtue of their experience, the most knowledgeable Mars experts in human history, and their knowledge, communicated back to Earth despite the delay, changes what the second mission looks like. If the first mission goes well, the second mission goes better prepared. If the second mission goes well, the third goes better still. Over a period of years to decades, what begins as an extraordinary, dangerous, uncertain undertaking gradually becomes less extraordinary in the sense of less unprecedented. though it may remain extraordinary in other senses for a very long time. The first ocean crossing was far more dangerous than the 100th. The first flight across the Atlantic was far more uncertain than the 1,000,000th. The first Mars landing will be far more uncertain than the 51st, but the first has to go first. Someone has to be the one who finds out what it is actually like. Someone has to be the one whose experience shapes everything that comes after. And the honest, considered possibility that the first humans to reach Mars may never return is, in this light, not a prediction of tragedy, but a recognition of what being genuinely first means. Being first means going before the knowledge exists that would make the going safer. It means accepting the uncertainty so that those who come later can inherit the reduced uncertainty. It means, sometimes, not coming back. There is a particular kind of reflection that this topic invites, one that connects the specific situation of the first Mars explorers to something broader about the human relationship with risk and meaning and the desire to do things that matter. The history of our species is, among other things, a history of choosing the hard thing, of crossing the unknown water, of climbing the unclimbed mountain, of going into the unlit cave, of asking the question that might not have a comfortable answer. This tendency to move toward the difficult and the unknown rather than settling into the familiar and the safe has not always served us well in its individual instances. It has killed many people who might otherwise have lived long and comfortable lives. It has led to suffering and loss and grief that did not need to happen. But in aggregate, over the long arc of the species, this tendency has brought us to where we are. The willingness of specific people in specific moments to go somewhere they might not come back from, to do something that had not been done before, to risk the certain comfort of the known for the uncertain promise of the unknown, is inseparable from the story of how we came to be the kind of creature that can look at a reddish point of light in the night sky and build a machine to go there. The first humans who reach Mars will be part of this long story. Their going, their willingness to accept the possibility of never returning will not be a departure from human nature. It will be an expression of one of human nature's most defining characteristics: the capacity to choose meaning over safety, to choose the horizon over the hearth, to choose going over staying when the thing at the end of the going seems worth more than the certainty of remaining. And from the perspective of the species, of the long trajectory of human civilization and its relationship with the universe, the first Mars landing, with all its difficulty and all its danger and all its honest possibility of not coming back, may be one of the more important things we ever do. Not because Mars will be easy to live on. It won't. Not because the return will be guaranteed. It may not be. But because going there, in the face of all that difficulty and all that danger, and doing the work that needs to be done to begin to understand what is there and what it means for us to be there, is the next extension of a story that has been building for as long as human beings have been able to look up and wonder. Let's bring together the threads of this long exploration as we move toward its close. We have established that a Mars mission is long and the return journey is genuinely difficult. We have explored the biological challenges, the radiation, the microgravity effects, the medical limitations, the psychological weight of extreme isolation and extreme distance. We have thought about the ethical dimensions of choosing to go to a place you might not return from, and the additional ethical complexity introduced by the possibility of permanent settlement and the children who would be born there. We have considered the scientific case for going, the possibility of finding evidence of ancient life, the geological and atmospheric and planetary science questions that only Mars can answer. We have thought about who would go, the specific kind of person drawn to this specific kind of challenge, and the genuinely coherent value system that might make permanent residency on Mars not a tragic default, but a chosen aspiration. And through all of this, the honest statement in tonight's title has, I hope, become something richer and more nuanced than it might initially have appeared. The first humans to reach Mars may never come back, not merely because something might go wrong, but because the genuinely first mission to anywhere genuinely new is conducted under conditions where coming back is uncertain rather than assured, where the risks are real and the engineering margins are not yet generous, and where some fraction of the people who choose to go may choose to go specifically because the going matters more to them than the returning. This is not a small or comfortable truth, but it is an honest one, and sitting with it carefully, as we have tried to do tonight, reveals something about the genuine texture of human ambition and human courage and human choice that the simplified versions of this story tend to leave out. As the night settles around you and the day's concerns begin to fade, let's hold one final image from everything we have explored. Somewhere on Mars, perhaps within your lifetime if you are young, and certainly within the lifetime of someone alive today, a person will take a step. Not a metaphorical step, but a literal one. A boot will press into Martian regolith, the rust-red surface dust of another planet, and a human footprint will be left there. That person will look up and see an earth-colored sky, Martian blue near the horizon, fading to pink, fading to the dark butterscotch of a Martian midday, and they will know with a certainty that no one before them has ever had in quite this form that they are somewhere genuinely new. They will have traveled 6 months or more to get there. They will be far from anyone who loves them in a way that no form of communication can fully bridge. They will be in a suit because the air outside it would kill them in minutes. They will be performing a task, some scientific observation or some equipment check or some assessment of the landing site, because the mission does not pause for reflection even when reflection is overwhelmingly available. And they may know, or they may not quite let themselves know, that the road back is uncertain, that the vehicle that will carry them home has to work perfectly, that the fuel has to have been made correctly, that the window has to open when it should, that their bodies have to hold up, that everything has to go right, and they may know, or they may quietly hold without quite saying, that for them personally, the going was worth it. That this moment, this footprint, this sky, this distance, this specific and unprecedented situation of being exactly here was worth more than the certainty of staying. That wherever this road ends, they are glad they took it. If there is something in this story that feels worth sitting with as you rest, some quiet recognition of the genuinely extraordinary thing that is approaching in the human story, or some appreciation for the people who will choose to face it in ways that most of us will only ever read about, then tonight's exploration has done something of what it was meant to do. You are welcome to return to beyond the cosmos whenever curiosity calls you back, toward the universe's great questions, toward the human story within it, toward the careful, slow, patient exploration of what all of this means. There is always more to explore. For now, let the reddish point of light in the imagination settle. Let the weight of the day finally release. Rest here, in this warm and blue-skied corner of the solar system, in the full knowledge that this is not the last place our kind will sleep, and that the first person to sleep on Mars is probably already alive, somewhere growing toward the extraordinary choice ahead of them. Let's go back and spend considerably more time on the engineering of the return journey, because the physical and technical specifics of getting off Mars and back to Earth deserve a thorough examination that goes beyond the brief sketch we drew earlier. The details matter here because they are what determine the actual probability of return, and because understanding them honestly is what allows us to appreciate both the difficulty of the challenge and the ingenuity being brought to bear on solving it. The first constraint is the launch window. Mars and Earth orbit the Sun at different distances and at different speeds. Earth, being closer to the Sun, orbits faster. Mars, being farther out, orbits more slowly. As a result, the relative positions of the two planets change continuously, cycling through a full range of alignments roughly every 26 months. Every 26 months, there comes a period of relative closeness and favorable alignment called an opposition, during which the delta V, the change in velocity required to travel between the planets, is minimized. Missions to Mars are planned to launch during these windows, and return missions are similarly planned to take advantage of return windows that typically open roughly 14 to 22 months after arrival, depending on the specific orbital mechanics of the year in question. If the return window closes without a successful departure from Mars, the crew must wait for the next window, approximately 26 months later. This means that a malfunction of the return vehicle discovered shortly after the window closes could strand the crew on Mars for an additional 2+ years beyond the planned mission duration. Whether their life support, their psychological resilience, and their supplies can sustain them through that additional period is a genuine mission design question, and it is one of the reasons that Mars mission architectures typically include substantial margins in supplies and life support capacity beyond the nominal mission duration. The return vehicle itself presents multiple categories of technical challenge. Its propulsion system must work perfectly after being exposed to Mars's environment for whatever duration the surface stay involves. That environment includes temperature swings of more than 100 degrees Celsius between day and night, dust storms that coat every exposed surface with fine abrasive particles, and background radiation that, while much lower than interplanetary space due to Mars itself providing partial shielding, still represents a radiation environment that electronic systems must be designed to tolerate. The fuel for the return journey, whether carried from Earth or manufactured on Mars, must be stored safely through these conditions and still be usable when the time comes. Cryogenic fuels, liquid hydrogen and liquid oxygen being the most energetically efficient combination for rocket propulsion, are particularly challenging to store in a planetary environment for long periods, since they require active cooling to prevent boil-off. Methane and liquid oxygen, the propellant combination that SpaceX's Raptor engines use, and that is compatible with on-Mars manufacture through the Sabatier reaction, are somewhat less challenging to store cryogenically, but still require careful thermal management over extended periods. The structural integrity of the return vehicle also requires attention. A rocket that has been sitting on a planet's surface for a year or more has been subjected to thermal cycling, dust, and potential mechanical stress from Marsquakes or from the settlement of the surface beneath it. A rocket that launches from Earth is launched within weeks of final assembly and inspection. A rocket that launches from Mars may launch after a year or more of exposure that cannot be fully anticipated during design. Comprehensive inspection before launch is possible, but limited by what tools the crew has available and what can be confirmed from visual and instrument examination rather than full structural testing. These are not arguments that a Mars return mission cannot be done. They are arguments for why it is genuinely difficult and why the engineering margins matter enormously. Every additional kilogram of redundant systems, every additional backup capability, every additional design margin buys additional probability of success. The question, always, is what probability of success is acceptable and what resources are required to achieve it. The fuel manufacturing question on Mars deserves its own careful exploration because it is one of the more remarkable pieces of engineering being seriously planned for Mars missions. And it also illuminates why early missions might genuinely face a moment of uncertainty about whether return fuel has been successfully produced before the crew even arrives. The basic chemistry is well established. Carbon dioxide, which makes up about 95% of Mars's atmosphere, can be combined with hydrogen to produce methane and water vapor through the reaction known as the Sabatier reaction. The water can be electrolyzed using electrical power to produce hydrogen and oxygen. The hydrogen is recycled back into the fuel production process and the oxygen is accumulated. The methane that is produced can be stored as a liquid rocket propellant by chilling it to below approximately -161 degrees Celsius. The oxygen, also stored cryogenically, serves as the oxidizer for the rocket engine. This process requires a source of hydrogen, which Mars does not have in convenient atmospheric form. The hydrogen must either be shipped from Earth, adding to the mission mass, or extracted from Martian water ice, which is available but requires extraction and electrolysis. It requires substantial electrical power, either from nuclear fission reactors or from solar panels, to drive the electrolysis process and maintain the cryogenic storage. And it requires reliable, autonomous operation over months to years, since the fuel production plant would need to be delivered to Mars and begin operating well before the crew arrives. One mission architecture, which NASA has studied and which SpaceX has incorporated into elements of its planning, involves sending the fuel production system and potentially a preloaded return vehicle to Mars on an uncrewed mission 1 or 2 launch windows before the crewed mission. The fuel production system operates autonomously during the 26 months before the crew arrives, manufacturing and storing the return propellant. By the time the crew lands, a fully fueled return vehicle is waiting for them, having been manufactured on Mars from Martian resources during the intervening period. This is an elegant solution to the mass problem, but it introduces a different class of risk. The crew's return depends on a system that has been operating autonomously on another planet for years and that cannot be inspected or verified in real time before the crew commits to the journey. Robotic precursor missions and extensive testing on Earth can reduce this risk substantially, but they cannot eliminate it. There will be a moment in any Mars mission that depends on on-site fuel production, when the crew confirms that the fuel is ready and the return vehicle is go for launch, and that moment will carry a weight of verification and inspection and cross-checking that will be, for the people involved, one of the most consequential moments of the mission. There is a dimension of this story that we have not yet explicitly examined, and it concerns the people who will not go. The mission support teams on Earth, the families of the crew, and the broader public that will be watching. A Mars mission is not conducted by the crew alone. It is conducted by an entire civilization's accumulated technical expertise, channeled through a team of thousands of engineers, scientists, flight controllers, psychologists, logistics specialists, medical consultants, and others, all of whom spend years preparing for the mission and then supporting it in real time from Earth, constrained always by that irreducible communication delay. The people in mission control for a Mars landing will be people who have dedicated years of their professional lives to making that landing possible. They will include engineers who designed systems they will never personally see operate in the conditions they were designed for until the mission flies. They will include flight controllers who have drilled for contingencies they hope never arise and trained for anomalies they hope are theoretical rather than real. They will have thought repeatedly and carefully about what they do if something goes wrong in a way that they cannot help fix in real time. The families of the crew face a different but equally real set of challenges. A family member who sends someone to Mars knows that they are sending them on a mission with a round trip that is not guaranteed, that communication will be delayed in ways that make real-time emotional support impossible, and that the person they love is living in a situation of danger and hardship for which proximity and support are simply unavailable. Every message from Mars that arrives at a home on Earth carries with it the knowledge that it was sent many minutes ago, that the person who sent it has already experienced whatever came next before their words have even arrived, and that the next news from Mars might be good or might be otherwise. The families of astronauts on long-duration ISS missions already experience a version of this, and what they describe is a particular kind of love conducted at a distance, supported by regular communication, but shaped by the knowledge of risk and the inability to do anything about that risk from Earth. A Mars mission extends this experience in both duration and distance by an order of magnitude, and the specific possibility that the crew may not return adds a dimension that ISS families, whose crew members return to Earth after 6 months with high reliability, do not typically face in the same way. What this means for mission design and for the human systems that support a Mars mission is that the psychological support extended to the crew cannot be decoupled from the psychological support extended to the crew's families and to the mission support teams themselves. The human cost of a Mars mission is not only the experience of the people on Mars, it is the experience of the entire community of people connected to them. Let's think now about the history of extreme exploration more carefully, because the context it provides for tonight's discussion is both illuminating and genuinely emotionally resonant, and because drawing the parallels carefully rather than loosely helps us see both where the Mars analogy holds and where it breaks down. The Apollo program remains the closest historical precedent for a crewed mission to another world, and its history is instructive in multiple ways. The crew of Apollo 11, Neil Armstrong, Buzz Aldrin, and Michael Collins, was fully aware that the lunar module's ascent engine, the system responsible for lifting Armstrong and Aldrin off the lunar surface, was a single-string system with no backup. If the ascent engine failed to ignite, the crew on the surface had no rescue option and no return. Richard Nixon's speechwriter prepared a speech to be delivered in the event that this happened, a speech that acknowledged the men had given their lives and that the gates of the moon would be shut on them forever. The failure did not happen. But the possibility was real, acknowledged, and accepted. This was not an exceptional feature of the Apollo program. It was a defining feature of every early phase of human spaceflight and of every phase of genuinely pioneering exploration before that. The crews of the early Antarctic expeditions traveled to a place where, if something went wrong badly enough, no help could reach them before they died. This was understood. The expeditions went anyway because the knowledge that could be gained and the precedent that could be set were considered worth the risk by the people who bore that risk. What distinguishes the Mars mission from the Apollo precedent in terms of risk profile is primarily duration and distance. The lunar surface is 3 days from Earth. The International Space Station is a few hours from Earth. Mars is 6 to 9 months from Earth under the best circumstances. The longer the duration and the greater the distance, the more opportunities exist for things to go wrong, and the less capability exists for anything to go right if they do. This is the fundamental logic that makes the Mars return problem genuinely more serious than any previous human spaceflight return problem. But the spirit of the people involved, the willingness to go knowing that the return is not guaranteed, that specific spirit is not new. It is ancient, as old as the first human beings who left the territory they knew and traveled into territory that had no human footprints. It is one of the oldest and most consistent aspects of the human character, the willingness of certain people to go, knowing that going might mean not returning. Let's think carefully about what successful Mars missions might look like in a sequence of progressions, because the first human Mars landing will almost certainly not be the last. And thinking about how the risk profile evolves over successive missions helps frame the question of who goes first and under what conditions. The first crewed Mars mission, whenever it occurs, will be the most uncertain and most risky. Every system will be operating in the actual Martian environment for the first time with humans depending on it. Every assumption built into the mission design will be tested against reality rather than against simulations or Earth-based analogs. The crew will discover things that the engineers did not anticipate, both problems and solutions. Some of what they discover will be manageable on the fly. Some will require the ingenuity and determination of 6 people a very long way from help. Assuming the mission is successful or sufficiently successful that the program continues, the second crewed Mars mission will benefit from everything learned on the first. The systems that proved reliable will be retained. The systems that showed weaknesses will be redesigned or supplemented. The specific environmental challenges that were underestimated will be better accounted for. The psychological and interpersonal dynamics that proved challenging will be better prepared for. The medical situations that arose will be incorporated into training and mission medical kits. Over 5 to 10 missions, assuming a sustained program, the risk profile of a Mars mission changes substantially. Not to the level of routine, which is a word that will be inappropriate for a Mars mission for a very long time, but to a level where the specific failure modes are better understood, the specific environmental challenges are better prepared for, and the specific return journey risks are better mitigated by design improvements driven by experience. The first people to go to Mars will therefore accept the highest risk in the entire history of the program. They are the ones who discover what was not anticipated. They are the ones who demonstrate what actually needs to change. They are the ones whose experience makes the subsequent missions possible. In this sense, the first Mars crew occupies a particular role in the history of their program that is both the most dangerous and the most important. There is a philosophical dimension specific to the one-way possibility that is worth examining more carefully, because it concerns the relationship between finitude and meaning, a relationship that runs throughout human experience but takes an unusually concentrated form in the specific situation of a Mars explorer who accepts that they may not return. Human beings are mortal. Every human life is a one-way journey in the sense that no one comes back from it. This fact sits at the center of most serious philosophical and religious traditions which have grappled with what it means to live a finite life in various ways, most of which resolve in some version of the idea that the finitude is what gives the life its meaning. An infinite life would not have the urgency, the preciousness, the weight of choice that a finite one has. The very fact that our time is limited is what makes the specific use of that time matter. The person who goes to Mars with the possibility of never returning is not in a categorically different situation from every other human being in this respect. They are in a situation where the finitude is brought closer, made more concrete, made undeniable in ways that it tends to be deniable in ordinary life. The average person going about their daily business can maintain, most of the time, the comfortable fiction that death is far away and abstract. The person on a spacecraft 6 months from Earth, knowing that a failure of the return vehicle would make their current location their final location, cannot maintain this fiction so easily. What many accounts of people who have faced genuinely extreme risk, mountaineers above 8,000 meters, solo ocean rowers, polar explorers in genuine extremis, suggest is that this confrontation with the concreteness of possible death does not typically produce despair. It produces clarity. The peripheral concerns, the small anxieties, the social performances and minor competitive worries that fill ordinary life tend to fall away in conditions of genuine extremity, leaving behind what actually matters to the person in question: their work, their companions, the specific beauty of where they are and what they are doing. If this is right, and there is substantial experiential and psychological evidence that it is, then the people on a Mars mission, living daily with the knowledge that their return is not guaranteed, may be living with a particular kind of intensity and a particular kind of clarity that most human experience does not produce. Not comfortably, not easily, but genuinely, and with a depth of presence that the cushioning of ordinary safety prevents in most ordinary lives. This is not an argument for making Mars missions more dangerous in order to produce this psychological effect. It is an observation about what extreme, consequential undertakings do to the inner life of the people who engage in them, and about why the possibility of not returning, for certain people in certain contexts, is not simply a cost to be minimized, but an aspect of the experience that shapes its meaning. Let's turn our attention to what happens in the years and decades after the first successful Mars mission, particularly from the perspective of how humanity's relationship to Mars shifts. The first successful human Mars landing and return, or the first successful human Mars landing and permanent settlement, changes the subjective human relationship to Mars permanently. Mars goes from being, in the most literal sense, beyond human experience, an object of observation and inference and robotic exploration, but never of direct, lived human experience, to being a place where people have been. A place where human feet have walked, where human voices have spoken into Martian air, where human eyes have watched Martian weather unfold over a landscape that no human eye had previously observed from within. This transformation is not trivial. The history of human attitudes toward places that no human being had yet been suggests that direct human experience changes not just our technical knowledge of a place, but our entire relationship to it. Antarctica before the first expeditions and Antarctica after the first expeditions are not the same conceptual object in the human imagination, even though Antarctica itself was unchanged by the expeditions. Mars after the first human landing will be different in this subjective way. Not physically different, but different in terms of what it represents in the human understanding of the possible. Every subsequent Mars mission will find Mars a somewhat different conceptual object than the first mission found it. Not more accessible in a physical sense, because the physics of the journey does not change, but more imaginable, more specific, more known in the way that direct human experience makes things known that data and images and robotic samples cannot quite achieve. The stories that the first Mars explorers bring back or send back will be of a different kind than the stories told by the Perseverance rover or the Ingenuity helicopter. Not because those robotic instruments aren't remarkable, but because human stories of human experience in a place carry a specific kind of meaning that the most sophisticated robotic report cannot replicate. Let's spend time now on the question of whether and how and to what extent the people who are thinking seriously about Mars missions have grappled publicly with the one-way possibility and what they have concluded or implied in doing so. Elon Musk, whose company SpaceX has made Mars missions a central long-term goal and whose Starship vehicle is specifically designed with Mars in mind, has spoken publicly and at some length about the one-way possibility, and his statements on the subject are revealing not just as individual opinions, but as indicators of how the most serious private sector effort in Mars exploration understands the question. Musk has said in various public forums over the years that the first Mars missions will be dangerous. He has said that he would not be surprised if people die during the early missions, and that this is a reality that serious Mars exploration has to acknowledge rather than avoid. He has also discussed, in more than one context, the idea that Mars colonization is likely to involve people who are willing to accept a high risk of death as the price of being among the founders of a Mars civilization. In at least one widely reported interview, he described the first Mars missions as comparable in some ways to the Shackleton expedition, not in the sense that death is the goal, but in the sense that the risk is real, acknowledged, and considered acceptable by those who choose to go. NASA's public communication on the subject has tended to be more cautious, as one would expect from a government agency that is accountable to a public and a Congress that generally expect its human spaceflight programs to bring astronauts home safely. NASA's official position on crewed Mars missions has consistently emphasized the development of technologies that would make a round trip feasible, and safe, rather than exploring the one-way mission architecture as a primary option. This does not mean that NASA's engineers and mission architects have not thought carefully about the one-way scenario. It means that the public-facing communication has tended to frame the goal as minimizing the risk of one-way outcomes rather than embracing them as part of the mission architecture. The Mars Society, a non-profit organization founded by aerospace engineer Robert Zubrin in 1998, has been a consistent and detailed advocate for human Mars exploration, and Zubrin's Mars Direct mission architecture, first outlined in the early 1990s, has influenced Mars mission planning significantly. Zubrin has consistently argued for architectures that include return capability as a fundamental design requirement, not because the one-way scenario is unthinkable, but because he believes the credibility and long-term sustainability of a Mars program depends on demonstrating that the program can bring its crew home. What emerges from surveying these different perspectives is a general acknowledgement across the spectrum of serious Mars exploration advocacy that the return journey is the hardest part, that early missions will carry real risk, that the return will be delayed or fail entirely, and that the specific individuals who go on the first missions will need to accept this uncertainty as part of their informed consent to the mission. There is a particular and important question that the title of tonight's exploration implicitly raises, and it deserves to be asked directly. What would it mean for humanity if the first Mars crew did not come back? Not in the sense of what the engineering lessons would be, or what modifications would be made to subsequent missions, though those questions are important, but in the deeper sense of what it would mean for the human spirit, for the way we understand ourselves and our relationship to the cosmos, if a crew of human beings traveled to Mars and died there. The answer to this question is, historically speaking, available to us in some degree, because we have seen what happens when explorers die in the course of genuinely pioneering expeditions. Robert Falcon Scott and his companions died returning from the South Pole in 1912. The 3 crew members of Soyuz 1 died in 1967. The crew of Challenger died in 1986. The crew of Columbia died in 2003. In each case, there was grief, and there was a period of examination and reassessment. And then, with varying timescales, the program continued. The grief was real. The loss was real. The examination was necessary and productive, and the continuation was also real, because the people involved and the communities that supported them understood that the goal that had inspired the mission was not extinguished by the loss. A crew that died on Mars would be a different kind of loss than any previous spaceflight loss, both in scale and in character. The distance and the duration and the absolute impossibility of any intervention would give the loss a specific quality that Challenger and Columbia did not have, where the loss, however traumatic and however devastating, occurred near enough to Earth that the aftermath could be physically attended to. People who died on Mars would be unreachable, physically unreachable, in a way that no previous spaceflight loss has been. But the historical pattern suggests that even such a loss would not, by itself, end human Mars exploration. It would reshape it, and profoundly. It would deepen the urgency of solving the specific problems that led to the loss. It would change how subsequent missions are designed and who is selected for them. It would carry an emotional and cultural weight that influenced the program for decades. But if the case for Mars is strong enough to send people there in the first place, a loss, however terrible, would likely strengthen the determination to make the next mission work rather than permanently end the attempt. This is not callousness. It is the honest, observed pattern of how communities respond to the loss of people who died doing something important and dangerous in service of a goal that the community believes in. The loss is honored. The goal is pursued. The two are not in contradiction. Let's think now about the generation that will actually go, because they are, in a very real sense, already alive, and thinking about them as real people rather than as abstract future explorers adds something important to the texture of this conversation. The first humans to reach Mars, under any of the realistic timelines discussed today, are most likely people who are currently somewhere between childhood and early adulthood. They are growing up in a world where Mars missions are being seriously planned, where the Perseverance rover is sending back images of the Jezero crater in extraordinary detail, where Ingenuity has flown multiple times in the thin Martian air, where SpaceX's Starship is being developed and tested with Mars explicitly as a long-term destination, where space agencies around the world are maintaining Mars as a declared human exploration priority. They are growing up with Mars in their awareness in a way that previous generations could not quite access, not because previous generations lacked the imagination, but because previous generations lacked the context of an active, progressing program that was clearly moving toward a crewed mission rather than merely aspiring to one in some indefinite future. For a child or young person today who is drawn to the idea of going to Mars, the path there is beginning to look like a series of steps that could conceivably be walked rather than a single impossible leap across an unbridgeable gap. Some of these people will become astronauts. Some of them will become engineers who design the systems that others fly on. Some of them will become scientists who analyze the data returned from Mars and shape the questions that subsequent missions try to answer. Some small subset of them will be among the first to go. And among that small subset, a further small subset may be the ones who, by the specific timing of their mission and the specific contingencies that arise, face the genuine, individual, life-defining question of whether they are coming home. They are, these people, somewhere in the world tonight, doing what people do. Sleeping, perhaps, studying, working. Looking up at the night sky with something of the feeling that this channel tries to evoke and hold, the particular mix of wonder and ambition and humility that a clear night sky tends to produce in certain kinds of people. They don't know yet, most of them, that they are among the ones who will go. As we move toward the final moments of tonight's exploration, let's hold the full shape of what we have been discussing, drawing the threads into something close to a complete picture. Mars is genuinely reachable. The engineering challenges are real and formidable, but not physically impossible. The biological challenges are significant, but not, with careful mission design and crew selection, insurmountable. The psychological challenges are genuinely novel and genuinely difficult, but manageable by the right people with the right preparation. The return journey is the hardest part, involving fuel production or transport challenges, vehicle reliability challenges, and window timing constraints, each of which is addressable in principle and each of which will be addressed in practice before anyone is sent. And yet, the honesty of the title remains. The first humans to reach Mars may never come back, not because we have failed to solve the engineering, but because the first mission to anywhere genuinely new is the mission that finds out what was not anticipated. It is the mission where the margins are thinnest and the unknowns most consequential. It is the mission where the people involved are, by definition, the most experienced people in the world at dealing with the Mars-specific challenges of their mission, because no one has done it before, and they are the first people doing it now. And in that context, the specific failure modes that ground tests and simulations could not fully anticipate become the specific failure modes that the crew encounters without a manual for their resolution. The possibility of not returning is not a failure of preparation or imagination or will. It is the nature of being genuinely first. And the people who go first to Mars will understand this, as the people who have always gone first to genuinely new places have understood it. not as a reason not to go, but as the specific and honest texture of the choice they are making. One last thought before the night fully settles. There is a particular kind of quiet courage that is different from the dramatic, headline-capturing courage of obvious bravery. It is the courage of people who have looked at something carefully, who have understood it as well as it can be understood, who have sat with the probability distribution of outcomes and the full range of what could go wrong, and who have then, calmly and deliberately, chosen to do it anyway. The first humans to reach Mars will have that kind of courage. Not the courage of people who don't understand the risk. Not the courage of people who are carried forward by enthusiasm before the full weight of the situation has landed. But the courage of people who know, perhaps better than anyone on Earth does, exactly what they are doing and exactly what it might cost them. And when that first boot presses into Martian regolith, and that first human being stands on the surface of another planet and looks up at a sky that has never held a human gaze from within, some part of what we are as a species will be in that moment. Not just the technical achievement, though the technical achievement will be extraordinary. Not just the scientific knowledge, though the knowledge will be immense, but the specific and irreplaceable fact of having chosen to go somewhere that choosing to go might mean not choosing to come back and going anyway. That choice, made by specific people who are somewhere alive right now, has always been one of the things that has moved our species forward. Mars is the next place where it will be made. Rest now. The reddish point of light will still be there tomorrow, and beyond that, if you let yourself look, the people who will someday stand on it are still growing into the ones they will become. There is a dimension of the Mars mission story that we have only touched on, and it concerns the role that failure, partial or complete, plays in the historical record of exploration and what that tells us about how to think about the possibility of not returning from Mars. The history of exploration is not a history of unbroken success. It is a history of repeated, sometimes catastrophic failure punctuated by eventual success, often achieved by people who were not deterred by the failures of those who went before them, and sometimes were actively inspired by those failures to understand the challenge more completely and approach it more carefully. The first expeditions to the geographic South Pole included Scott's team, which reached the pole and then died on the return journey. That death, however devastating for the people involved and the communities that loved them, was also a body of information about what the Antarctic actually required, information that shaped every subsequent polar exploration. The early history of aviation is similar. Countless early aviators died attempting things that aircraft of the era could not reliably do, and each death was, among other things, a source of data and understanding that eventually made the next aircraft more capable and the next attempt more informed. The Wrights succeeded in part because they studied the failures of those who preceded them with more care than any previous experimenters had applied. This does not romanticize failure or treat the death of explorers as simply the cost of progress. Each person who died in the course of exploration was a person with a life and relationships and a future that was cut short. The tragedy of their death is real. But the context in which they died, in service of understanding something genuinely unknown, in the course of an attempt that was made as carefully and as competently as the state of knowledge allowed at the time, gives their death a specific character that is different from, say, death through negligence or through failure to account for known risks. If a first Mars crew does not return, the specific nature of that not returning matters enormously. If it results from a catastrophic failure that was entirely unforeseen and unforeseeable, it contributes information to the understanding of what Mars missions actually require and shapes the design of every subsequent mission. If it results from a failure that, in hindsight, was preventable with better preparation or better engineering, it contributes a different but equally important lesson. In either case, the loss would not be meaningless. It would be in the specific way that losses in the course of genuine exploration always are, part of the process by which the genuinely unknown becomes the known. This is not comfortable to say and not comfortable to hear. It asks something of us as listeners, an acceptance of a kind of tragic possibility that sits uncomfortably with the ordinary expectation that scientific and technological progress should, at each step, be safer than the last. But Mars is not the next step from ISS in the way that ISS was the next step from Mir. Mars is a genuinely different kind of challenge, in a genuinely different category of distance and isolation and duration, and the first people who go there will be, in a very real sense, going somewhere that no amount of Earth-based preparation can fully simulate or prepare them for. Let's explore the psychological dimension of the return uncertainty from a different angle, one that concerns not just the individual crew members, but the dynamic between them that a Mars mission will create and require. A crew of 4 to 6 people confined in a space comparable in volume to a large recreational vehicle or a small apartment, traveling for 6 to 9 months and then living and working on another planet for an extended duration, will develop a group dynamic unlike any other in human experience. The closest analogues, Antarctic winter overcruise, submarine crews, and long-duration ISS crews, all provide partial models, but none replicates the full combination of factors that a Mars mission involves. The specific factor that is most novel is the absolute unavailability of any outside arbitration or support in the event of serious interpersonal conflict. On a submarine, the captain has the authority to confine crew members or alter the mission if conflict becomes unmanageable. At an Antarctic winter over station, at least until emergency evacuation is possible in the warmer months, the station commander has similar authority. On the ISS, any situation that becomes truly unmanageable can, in principle, be addressed by returning the affected crew member to Earth, even if this is practically difficult. On Mars, none of these options exist. Conflict must be managed within the crew, by the crew, using the resources the crew has for the duration of the mission. The research on group dynamics in isolated and confined environments suggests several consistent patterns. Trust and cohesion tend to be high initially, when motivation and novelty are also high. They tend to decline around the midpoint of a mission, when novelty has worn off and the end is not yet clearly in sight. They typically recover in the final phase of a mission when the end is genuinely approaching and the shared motivation of completing the mission strengthens the group's cohesion. This pattern, studied across Antarctic expeditions, submarine deployments, and space missions, is sufficiently consistent to be incorporated into mission design and crew selection criteria. For a Mars mission, the specific challenge is the duration. A mission that lasts 2 to 3 years, including transit and surface operations, is longer than any previous isolated group has been studied in truly analog conditions for the full duration. The midpoint effect, if it follows the pattern, would occur roughly a year into the mission, and the crew members experiencing it would be doing so in an environment where outside help is genuinely unavailable, where the stakes of their continued effective collaboration are existential, and where the individual and collective stress of their situation is not decreasing but ongoing. This is not a prediction of failure. It is a description of a genuine challenge that mission designers, crew selection specialists, and the crews themselves need to understand and prepare for as thoroughly as the engineering challenges. The people who go to Mars first will be people whose psychological profiles have been vetted with extraordinary care, and the mission design will attempt to account for the dynamics described above. But the honest acknowledgement is that we are extrapolating from imperfect analogues, and the specific combination of stressors on a Mars mission may produce dynamics that imperfect analogues did not reveal. There is another thread in the story of the return that is worth pulling, concerning what happens to the crews of a Mars mission if and when they return to Earth after a stay of a year or more in Martian gravity. A crew that has been in Martian gravity at 38% of Earth's for a year or more, coming on top of the 6 to 9 month transit in microgravity, will arrive back at Earth in a physiological state that requires careful attention. The return transit in microgravity will have added further bone density loss and muscle atrophy on top of what the Martian stay involved. The cardiovascular system will have adapted over the course of years to a combination of microgravity during transit and reduced gravity during the surface stay. Returning to Earth's full gravity will require, according to every physiological model we have, an extended and intensive period of rehabilitation and readjustment. The specific physiological effects of extended time in Martian gravity remain genuinely uncertain because no human being has experienced them. Martian gravity is not microgravity, so the specific adaptations that occur in full weightlessness, which are well documented from ISS missions, will not apply directly. But neither is Martian gravity the same as Earth gravity, so the physiological baseline maintained by daily exercise in Martian gravity will be different from what the same exercise would maintain on Earth. Bone density, muscle mass, cardiovascular capacity, and potentially neurological function may all be affected in ways that are currently modeled but not empirically tested. This physiological uncertainty is itself a reason why early Mars missions need to include comprehensive medical monitoring and be accompanied by equally comprehensive medical analysis of the returning crew. The first humans to return from Mars will be, in addition to being extraordinary explorers, the first members of a medical cohort whose data will be invaluable for planning subsequent missions. Their physiological experience of both the outward journey, the surface stay, and the return will be studied with the kind of thoroughness that NASA and partner agencies apply to every long-duration spaceflight, and the findings will shape the mission design and crew preparation protocols for every subsequent mission. Let's spend our final extended section on a question that this entire exploration has been circling around but has not yet addressed directly. What kind of civilization sends people to Mars, and what does the act of sending people to Mars say about the civilization that does it? The specific set of circumstances that would produce an actual crewed Mars mission, a convergence of political will, funding continuity, technical readiness, and cultural appetite for the specific kind of risk involved, tells us something important about the society that achieves it. It is not the kind of thing that happens without genuine, sustained commitment from a significant number of people at many levels of a society, from the engineers and scientists and flight crew to the funding bodies and the political systems that support them, and the public whose taxes or investment dollars sustain the work. The societies that have historically produced the most significant exploration undertakings have tended to be societies in a specific kind of dynamic relationship with possibility. Societies that have, at their particular historical moment, both the technical capacity for the undertaking and the cultural and political will to pursue it. The Age of Sail produced the explorations of Cook and Columbus, not purely because the ships existed, which they did, but because the specific social and economic and intellectual conditions of Europe in that era produced people who wanted to go and institutions willing to send them and return to benefit from what they found. The space race produced the Apollo missions not purely because the rockets could be built, which they could, but because the specific geopolitical and cultural conditions of the 1960s produced the will to build them and spend the enormous resources their construction required. A society that sends people to Mars will be expressing something about itself in the act. Something about its relationship to risk, to knowledge, to the future of the species, to the value it places on certain kinds of extraordinary individual choice. whether that expression is made by a nation-state pursuing geopolitical prestige, or by a private company pursuing a commercial vision of multi-planetary humanity, or by an international coalition of institutions pursuing a shared scientific goal. The act of sending people to Mars says, in the most concrete possible way, that this civilization has decided that Mars is worth the price of the attempt. And the price, as we have been exploring all evening, includes the honest, accepted, non-zero possibility that the first people who go may not come back. A civilization that can look at this possibility, discuss it honestly, design against it rigorously, and then send people anyway, is a civilization that has achieved a particular and perhaps unusual relationship to the scale of its own ambition. It is a civilization that has decided in the most consequential and irreversible way that civilizations make decisions, that the future it wants to be part of includes human beings on another planet. That civilization is assembling itself right now. It is imperfect and it is fragile, and it is moving unevenly, and it is arguing about the specifics. But it is assembling, and someday, perhaps within your lifetime, or certainly within the lifetime of someone currently alive, it will send the first of its people to Mars. Some of them may come back, some of them may not, but they will have gone. And in going, they will have changed, permanently and irreversibly, the story of what kind of creature we are. We are nearly at the close of tonight's exploration now, and before we rest, let's gather everything we have covered into something like a complete picture. We began with the basic physics of the Mars mission, the 6 to 9 month journey, the return window constrained by orbital mechanics, and the fundamental engineering challenge of a return trip that requires getting off Mars with a rocket that either came with the crew or was manufactured on Mars from Martian resources. We explored the biological reality of what the journey does to human bodies, the bone loss, the radiation exposure, the cardiovascular changes, and the uncertainty about what Martian gravity does to physiology over extended periods. We thought carefully about the psychological dimension, the isolation, the communication delay, the group dynamics in an environment where outside support is unavailable and exit is impossible. We explored the ethical complexity of the one-way mission, including the deliberate version and the accidental version, and the specific additional complexity introduced by the question of children who might be born into a permanent Mars settlement. We thought about who would go, the specific kind of person who chooses this specific kind of risk for this specific kind of purpose, and the value system that makes such a choice coherent and even beautiful in its own way. We thought about what a successful Mars mission means for the missions that follow it, and about what a failed return would mean for the program and for the people connected to the crew. We thought about the history of exploration and what it tells us about how communities respond to loss in the course of genuinely pioneering work. And we thought about what the act of sending people to Mars says about the civilization that does it. Through all of this, the honest core of the title has remained. The first humans to reach Mars may never come back. Not because the goal is impossible, or the attempt foolish, or the risk unacceptably high given the returns, but because genuinely first things are genuinely uncertain, because the margin between success and the alternative is thinnest when the attempt has never been made before, and because the specific people who choose to make that attempt will do so with full knowledge of this, as people throughout our history have always chosen to do the difficult thing with full knowledge of its cost. What remains after everything is something closer to admiration than to pessimism. The people who will go to Mars, whether or not they come back, will be among the most remarkable members of our species who have ever lived. Not remarkable because they are exceptional individuals, though they will be selected in part for exceptional qualities. Remarkable because of what they choose to do, the choice to go somewhere that might be a one-way journey in service of something larger than their own comfort and their own safety, in service of a future that other people, many generations of other people, will eventually inhabit. That choice is not reckless. It is the most deliberate and the most considered and the most deeply human thing a person can do. The night sky on a clear evening still shows that reddish point of light. It is exactly where it has always been, and it is exactly as far away as physics requires. And somewhere between where you are resting and that distant point of light, the future is assembling itself, one careful, courageous, human step at a time. One final thread before the silence settles completely, concerning something that is easy to miss in the engineering and the biology and the ethics and the history, the specific texture of the view from Mars. We have thought a great deal about what it costs to get there, and what it costs to stay, and what it means to possibly not come back. We have thought less about what is there, waiting for whoever arrives. Let's give that its due. Mars has mountains. Olympus Mons, the largest volcano known in the solar system, rises roughly 22 kilometers above the surrounding plains, nearly 3 times the height of Everest above sea level, spreading across an area comparable to France. From a certain distance, its size is so vast that the curvature of Mars would hide its base from anyone standing on its summit. It is not visible as a mountain from below in the way that Earth mountains typically are. It is more like a vast raised plain, a continent of volcanic rock rising gradually but relentlessly from the surrounding terrain. Valles Marineris, the canyon system that runs along the Martian equator, stretches for roughly 4,000 kilometers, roughly the width of the United States, at depths of up to 7 kilometers in places and widths of up to 200 kilometers. It dwarfs the Grand Canyon in every dimension except perhaps in the specific colors and the specific light which the Grand Canyon has in abundance, and which Mars, with its different chemistry and its different sun, would render differently. The sunsets on Mars are blue. During the Martian day, the sky, seen by the Mars rovers and now documented in photographs, is a butterscotch or brownish pink because of the fine dust that permeates the atmosphere and scatters the light differently than Earth's cleaner oxygen-nitrogen air does. But at sunset and sunrise, when the sun is near the horizon and the light is traveling through more atmosphere, the scattering shifts and the sky around the setting sun turns a pale, otherworldly blue. The first human beings to watch a Martian sunset will see something that no human being has ever seen from within: a blue dusk on a red planet, the sun smaller and more distant than from Earth, setting behind rust-colored plains and ancient volcanic ridgelines. The stars from Mars on a clear Martian night will be brilliant. The thin atmosphere blocks very little light. The dust, when not stirred into a storm, settles enough at night that the view overhead is essentially the view from space, unfiltered by the thick, protective, light-scattering atmosphere that simultaneously shelters Earth's inhabitants and softens their view of the cosmos. Among those stars, very bright, a pale blue-white point of light will be Earth. And beside it, slightly fainter, the Moon. The first humans on Mars will be able to look up and see the Earth, and on that Earth there will be billions of people who cannot quite see Mars as more than a reddish point, looking up at a sky in which a dim, distant point of light holds the people they sent there. That distance, rendered visible in both directions, simultaneously intimate and incomprehensible, is perhaps the image to carry into sleep tonight. Two worlds looking at each other across 225 million kilometers of space, connected by radio waves that travel at the speed of light and still take 20 minutes each way, connected by the extraordinary fact that some members of one world chose to go to the other. Whatever the cost of the going, whatever the uncertainty of the return, that choice and that connection are genuinely extraordinary. And perhaps that is the place to truly close, with those two worlds looking at each other, not yet fully understanding the other, connected by the people willing to cross the distance between them. The first humans to reach Mars may never come back, or they may come back changed beyond what Earth can easily accommodate, changed by what they saw and felt and carried in that extraordinary distance. Or they may return and find that the Earth they knew looks different from the eyes of someone who has seen it as a pale point of light in an alien sky. Whatever they find on the return, if they find it, they will have gone. And in going, in that singular, deliberate, irreversible choice, they will have done the thing that the human species has always done at its most extraordinary: moved toward the unknown horizon, accepted the uncertainty of the going, and trusted that the going was worth it. Beyond the Cosmos will be here when curiosity calls you back. Whenever you want to sit with another of the universe's great questions, whether they concern the ancient cold of a distant nebula or the ancient drive of a species reaching for the next planet. There is always more to explore, and always here, a quiet space to explore it. For now, rest. The reddish point of light can wait. It has been waiting for as long as humans have had eyes to see it. It can wait a little longer. Good night.